Hello everyone, today we are going to present our project on neural networks. Project title is Deep Learning for Global Landmark Recognition. Coming to the motivation, this project aims to understand and categorize an image which is taken from the Google Landmark datasets under a specific landmark class and classify them under each classes. Coming to the project's flow, first we are going to download our images from the CSV files. Second, we are going to pre-process our data. Third, we are going to visualize our data using Python. And fourth, we'll present our baseline model. And fifth, we'll refine our baseline model into our final model. Coming to the dataset is a largely huge dataset. It contains roughly 500 million images, which is divided into training, validation, and testing. The dataset contains various URL IDs for landmarks and their corresponding landmark IDs. And this is how our images looks like. Coming to the data preprocessing, we are extracting our images using web scraping, and then we are resizing the images into 32 cross 32 to ensure we have a faster training. We have only taken 30,000 images which were spread across 500 classes to make the training easy. And this is how our data looks like. As you can see on the left, we are having landmark IDs, and we can see two columns, which is divided between ID and URL. Coming to our baseline model, we choose CNN as our baseline model because it was well suited for our visual data. CNN contains multiple layers that can be individually identified through various aspects of an input image. The complexity of CNN can vary greatly. It can contain various several hundreds and thousands of layers. We decided to choose CNN because it's a basic neural network model for our image classification tasks. And this is how a CNN architecture looks like. We have taken an input image. It will go through a feature extraction layer, which will contain of convolution and pooling layers. It will then go to the classification layer, which will flatten the input data. And lastly, we'll identify the output through probabilistic layers. This is how our stages in CNN looks like. As you can see, the input layer is an image. The feature extraction stage will contain image features, and the rest classification, probabilistic, and output stage comes later on. This is how our graph looks like. We got a training accuracy of 89.9% and validation accuracy of 57.1%. Coming to the final model, we have chosen ResNet because it's a very well pre-trained model. It's called ResNet 50 because it has 50 layers in its neural network. It's a powerful image classification model that can be trained on large datasets and achieve state-of-the-art results. This is how our ResNet 50 architecture looks like. Our input layer will go through convolution layers, and then it will batch normalize all the images, and it will go to the activation function layer and the max pooling layer. And we also have more complex layers in stage 2, 3, and 4. Finally, it will make an average of all the poolings and it will flatten the output data. Coming to the model, we have chosen ResNet 50 to address the challenges of training because our Google Landmark dataset has almost 5 million images, and traditional CNN can suffer from vanishing gradient problem when network becomes too deep, making it difficult to train effectively. Due to improved gradient flow and easier training, we have chosen ResNet 15 to converge our data faster during training compared to conventional CNN architectures. Coming to the model comparison, as we can see, CNN did a pretty fair job in training, but it's not very great in validation. But in ResNet 50, it improved the training accuracy as well as the validation accuracy. Coming to the conclusion, we are at a post-training stage with impressive training accuracy. As I said, validation accuracy can be improved furthermore, but we have to look for other models apart from ResNet 50. ResNet 50 model demonstrates that its superior performance. It has a superior performance compared to baseline CNN, suggesting it has more robust feature learning and better generalization capabilities. Coming to the future scope, we are prioritizing on validation accuracy before submitting our model, and we also kept an option open to explore other alternative models that offer better accuracy. We employed to deploy different techniques to bridge the gap between training and validation performance, and I hope it will also improve the validation accuracy. So, all in all, it is a mini data set because it only has 30,000 images. But if we had some more hardware resources, I think we can improve our validation accuracy more. Thank you.